This is the second lecture from the series Making Sense of QFT. The title is Wigner's Particles. I'm going to tell you about a remarkable physical theory which unifies quantum mechanics and the principle of relativity in the most beautiful and logical way. Here is the outline of today's talk. Last time we discussed the Poincaré group of inertial transformations and the quantum mechanical description of physics in the Hilbert space. By combining these two ideas, we will arrive at Wigner's theory of group representations. In this representation, generators in the Poincaré-Lie algebra are Hermitian operators. They can be interpreted as total observables of the physical system. We will see that Hilbert spaces of elementary particles correspond to reducible representations of the Poincaré group. And we will discuss how Wigner classified elementary particles by their mass and spin, and how one can write a relativistic analog of one-particle Schrödinger equation. For more details, you can check Chapter 2 of Weinberg's textbook and chapters 3 to 5 of the first volume of my book. In his works in 1930s, Wigner tried to answer a simple question. We know that inertial transformations change observer's point of view, but this change should be somehow reflected in the Hilbert space of the observed system. So the question is how state vectors and operators of observables are affected by inertial transformations. Wigner proved an important theorem which says that inertial transformations should be represented by unitary operators, U of G. There are two ways one can do an inertial transformation G. First, one can apply it in an active way to the system itself. Then the unitary operator U of G should be applied to the state vector. This is called the Schrödinger picture. Alternatively, the inertial transformation can change the point of view of the observer. Then the unitary operator U of G should be applied to operators of observables. This is the Heisenberg picture. To check the consistency of these formulas, let us now perform an inertial transformation on the entire laboratory. In other words, apply it to both the state preparation and measurement devices. According to the principle of relativity, measurements will not be affected in this case. And this is exactly what our formulas show. Wigner's theorem told us about a Hilbert space representation of a single inertial transformation. But we know that the set of all such transformations forms a group. A theorem due to Wigner and Bargmann tells that there must exist a unitary representation of the Poincaré group in the Hilbert space of the system. This representation can be either single-valued or double-valued. In the latter case, the state vector obtains a factor of -1 after full 360 degrees rotation. This is the first hint about the half-integer spin that will be discussed later. If the concept of group representation is new to you, let me give you a simple example. As an example of a group, let us take the group of translations in one dimension. The group multiplication law is very simple. Two successive translations for distances A and B are equivalent to one translation for the sum of these two distances. We're going to build an unitary representation of this group in a one-dimensional complex Hilbert space. Operators in this Hilbert space are one-by-one matrices, so they are just complex numbers. Unitary operators are unimodular numbers. They can be conveniently represented by exponents of imaginary arguments. Now, I claim that one possible unitary representation of the translation group is given by this formula. To each translation for the distance A corresponds an exponent of I times A divided by h bar. I have decided to use h bar as a factor here, but in fact I could choose any real constant. As we will see later, real physical representations of the Poincaré group always have h bar as a factor in the exponent. Let me now verify that this is indeed a legitimate representation. The product of representation matrices corresponds to the product of group elements. Check. The representative of the inverse translation is given by the inverse matrix. Check. And the representative of a trivial translation is the unit matrix. Check. We are done. Let's now return back to representations of the Poincaré group. In this case, 10 generators of the Poincaré-Lie algebra are represented by Hermitian operators, which are identified with physical observables of the total momentum, total angular momentum, Hamiltonian. The boost generator corresponds to the observable that is roughly equal to the product of the center of mass position and energy. Unitary operators of the group representation are exponential functions of the generators. The next point is that these Hermitian representatives satisfy quantum commutators that basically repeat the Lie brackets of the Poincaré-Lie algebra. The only difference is the presence of the product IH bar on the right-hand sides of these equations. So we immediately obtain quantum commutators between quantum operators of observables. We got them for free. They follow simply from symmetry properties of inertial observers. Isn't it cool? This construction helps us to answer a very important question. How to tell whether a specific physical theory is relativistically invariant or not? The necessary and sufficient condition for the relativistic invariance is that the Hilbert space has 10 Hermitian operators satisfying commutation relations shown here. It doesn't matter whether your theory has a covariant looking Lagrangian or field equations. If you cannot specify the 10 operators with the required commutators, then your theory is not relativistic. In what follows, when we talk about building an unitary representation of the Poincaré group, we actually mean constructing 10 Hermitian generators with the above commutators. These are actually two equivalent tasks, but constructing 10 operators is definitely easier than finding an infinite number of unitary representatives of the group elements. The 10 Poincaré generators correspond to the so-called basic observables. Wigner's theory makes a reasonable assumption that all other observables can be expressed as functions of the basic ones. Then it's not difficult to derive these functions, some of which are shown here. These are operators of the total mass, center of mass velocity, Newton-Wigner position, and spin. Then we obtain immediately how observables transform from one frame of reference to another in the Heisenberg picture. For example, the total momentum is conserved. This follows from the fact that the total momentum commutes with the Hamiltonian. Note that the transformation law of any observable can be always converted to a series of commutators, as in this example. Since we express all our observables through generators, and commutators of generators follow from the Lie algebra, there is no difficulty in calculating transformation laws. Here is another example. The total energy is conserved, simply because the total energy is the Hamiltonian, which commutes with itself. By applying time translation to the operator of position, we obtain that the center of mass moves with a constant velocity. No surprises here. Finally, it's not difficult to show that by applying the boost operator to velocity, we get the usual relativistic law of addition of velocities. Everything I told you so far was true for any physical system, however complex or simple. All observables were total. This means that they referred to the system as a whole. But we know that all physical systems consist of particles. Before learning how to describe compound systems, we should say a few words about Hilbert spaces of elementary particles. The theory of group representation distinguishes reducible representations whose operator matrices have a block diagonal form in some basis, and irreducible representations whose matrices always form a single block. Irreducible representations are, in some sense, the simplest. Wigner postulated that irreducible representations of the Poincaré group describe the simplest physical systems that don't have internal structure. They will be called elementary particles. Next, we can recall Schur's first lemma, which says that if in a space of irreducible representation an operator X commutes with all group representatives, then this operator is equal to a constant factor alpha times identity operator. Mathematicians know that there are only two independent operators that commute with all Poincaré generators. They are called Casimir operators. These are operators of the mass squared and the spin squared. Then, by Schur's lemma, these two operators act by simple multiplication in irreducible representations. Therefore, all irreducible representations can be classified by two real parameters, mass and spin. The full classification was worked out by Wigner. It seems that many types of Wigner's irreducible representations do not have counterparts in nature, but there are three types that can be associated with familiar physical systems. First, there are irreducible representations with positive mass. Their spin parameter can take values 0, 1/2, 1, 3/2, etc. The number of wave function components is 2s plus 1. The energy-momentum relationship takes the familiar relativistic form. The common spectrum of the momentum and energy of a massive particle forms a hyperboloid in the momentum-energy 4-dimensional space. Then there are massless particles which are characterized not by spin but by helicity tau. Their energy is proportional to the momentum. Today we know only one massless particle, the photon. In Wigner's theory, the photon is not elementary. Actually, its Hilbert space is reducible. It is a direct sum of massless Hilbert spaces with helicities -1 and +1. In a classical language, a photon is a combination of states with left and right circular polarizations. The last type is a Wigner elementary system with zero values of mass, spin, momentum, and energy. In the energy-momentum diagram, this representation corresponds to the single point in the origin. This physical system has all properties of the vacuum. From the above definitions, we can derive some simple but important consequences. For example, it follows immediately that the speed of a massive particle is limited by the speed of light. The speed of a massless particle is equal exactly to the speed of light. And by substitution to the velocity addition formula, we can prove that this result holds for all observers. In other words, we have derived the second postulate of Einstein's special theory of relativity. Returning to the space of a massive particle, we notice that 3 components of momentum and 1 component of spin form a full set of commuting observables there. So we can form a complete orthonormal basis from common eigenvectors of these 4 operators. In this basis, it's not difficult to find explicit forms for the matrices of the irreducible unitary representation. Space translations and time translations are diagonal in this basis. They simply multiply basis vectors by imaginary exponents. By the way, it follows from the last equation that momentum space single particle wave functions satisfy the following analog of the Schrödinger equation. This equation is valid for any spin. The action of rotations involve unitary matrices D of the rotation group representations, acting on the spin component. The boost formula is especially complicated. It involves the so-called Wigner angle, and we will see in future lectures that this transformation is the key to Weinberg's derivation of the free quantum field. The first message I wanted to deliver today is that Wigner's theory provides a complete description of a single elementary particle. It also tells us everything we want to know about total observables of any isolated system. But this description misses many important details. Yes, we figured out that the total momentum and energy of any system are conserved. And we know that the center of mass moves with a constant velocity. That's basically all we can say so far. The theory does not tell whether the system go through reactions, decays, or other internal processes. But these are the most interesting physical phenomena, and we would like to know more about them. In order to get an access to this information, we should learn how the system is composed from its constituent particles and how these particles interact with each other. The best answer to these questions are provided by Dirac's theory of relativistic form of dynamics. I'm going to tell you about this theory in my next lecture. Thank you.